We live in an era where there's an incredible amount of spatial data for things around the world. If you're interested in ecology, evolutionary biology, and genetics, you might be interested in mapping the spatial distribution of your target organism. If you're interested in biomedical field or human demography, you might be interested in mapping the spatial distribution of human populations or different sectors of the populations, like where all the centenarians distributed across the world. And so understanding how our uses and map spatial data is really important, especially considering the amount of data that is available at the global scale. Let's get started. I've got RStudio open. I want to create a new project in a new folder. And I want this folder to be called like Spatial Data. And it'll restart my R session. And now I've got this Spatial Data project. And it looks like I had already created it. And I also created a folder called Neon Airborne. So you'll want to pause the video, download the Neon Airborne data and unextract it. You need to uncompress it because RCAN is an extra step to import compressed folders. So go ahead and unzip it or uncompress it and then come back. In this tutorial, we'll be working with rasters. So there are two primary types of geospatial data. One is rasters and the other is vectors. Raster data is stored as a grid of values, which are rendered on the map as pixels, and those pixels can have different dimensions or different resolutions. So each pixel value represents an area on the Earth's surface, whereas vector data represents specific features of the Earth's surface, and attributes are assigned to those features. We'll focus on rasters this week. I want to create a new R script, and we want to start by importing the data. Let's call this object DSM. We'll be working with digital surface models as well as digital terrain models to calculate a canopy height model for vegetation across these neon sites. We want to import our raster using the raster function, and we want to call it, it's in this Neon Airborne folder, and it's called, we want the harv underscore DSM crop.tif. So TIFF files are a very common format for rasters. And this particular raster is from the Neon site at the Harvard Experimental Forest. And this is a digital surface model. So a digital surface model is let's look at it. Let's load. Could not find function raster. And that's because I didn't call the library raster. And you may have to install it using the install.packages function if you've never installed it before, and then load your library. So I might comment this out, install.packages, raster. Remember, you only have to install packages once, and then in future sessions, you only need to call library. You don't have to reinstall it each time. So we've called the library. Now we can import our data, and we see it here. And let's look at a quick plot of this raster, and that'll help as I define it. So what we're looking at is a digital surface model. It represents the elevation of the top physical point. And so we can see the greener, higher elevations. So at these, whatever the top point that was returned in a LiDAR flyover, these might represent trees or rocky outcrops. More typically, they're trees in this region. But because the digital surface model returns the highest elevation for whatever point, whatever structure that it hits, we need to know the terrain in order to calculate the canopy height, because we don't know if this elevation is in addition to the terrain that's underlying it. So we'll end up subtracting digital terrain model from a digital surface model to calculate a canopy height. And this would be the true canopy height for trees in this region. And by doing this, we'll demonstrate raster subtraction, as well as a few other features. The metadata of a raster is especially important. If we printed out the object name, we can see that it's stored as a raster layer. It has a certain number of rows and a certain number of columns. It has a resolution, and this is 1 by 1, but we don't know what the units are. The units are specified in this CRS, a coordinate reference system. Here they're UTM, so the units are in meters. So our resolution is 1 by 1 meter. So each pixel is 1 meter by 1 meter. And it also gives you the min and max values. That's often useful if you're trying to spot errors. Like maybe these values are really off, and then you might need to return to your original data set. We'll continue to use ggplot. So we'll continue using what we've been learning. And we know ggplot is useful for making really nice plots, and in this case, really nice maps combined with other figures. And we'll do 3 steps today. We'll do spatial work, so just importing raster files so far. We'll convert to a data frame because this is what ggplot works with, and then we'll make plots. So let's convert our digital surface model to a data frame so that we can use ggplot instead of this base plot function. And we'll call it into a data frame by using the as.data.frame function for DSM harv. And we need to specify that the XY coordinates is true because this raster does have XY coordinates. And now we can see that the first few rows of our data frame has X and Y coordinates, as well as the values that were stored in each pixel. Now we can use ggplot and the geometry raster, geom_raster. We want to call the data DSM harv data frame. And in the aesthetics, we want X equals to Y, Y equals to Y, X equals X, Y equals Y, and fill, we want I'm picking out the names of these columns here. I'm going to copy and paste, minimize my typing. Okay, and I'm going to go ahead and run. Could not find function ggplot because I didn't call it. So I'm going to add that ggplot too. Lots of errors today. And now I'm ready to run this command. And it takes a while because there are, it looks like 2.3 million observations. Because this is a data frame, we can treat raster values as if they're part of a normal table. So calling the X and Y values, X and Y coordinates, and the fill. So now we have this raster image within a ggplot, which gives us a lot of freedom for customizing how we want to visualize that data. So the digital surface model is elevation of the top physical point in a LiDAR flyover, whereas digital terrain model is the elevation of the ground. And we will create our canopy height model by taking the difference between the two rasters. So we need to import our digital terrain model using the similar call to raster, and it's in the airborne folder, and I don't know what it's called, so I'm going to navigate to that folder, and it has a similar format, but it's DTM, harv_DTM crop.tiff. And I'm going to create a new raster called CHM harv, and we can do raster subtraction. You can also multiply two rasters together, divide them, divide one by another. In this case, we want to subtract our digital surface model by our digital terrain model, and this gives the true canopy height. So the raster math happens on a cell by cell basis. So it's subtracting the elevation of our terrain from the elevation of the surface, and what's left behind is the tree canopy. Now let's graph this new raster by following the 3 rules. One is do the spatial work, and that's what we did in this line here. We did the raster math. Now we have to convert to a data frame. So ching harv df, we have to call this as .data.frame, chm harv, and because this is a raster, we need to specify that those xy coordinates are true. And now the third rule is to make the plot. So ggplot, I want to call a geom raster for my CHM harv df, and I will need to add aesthetics. So x equals the x column, y equals the y column, and fill equals, let's look at the first few rows of our CHM harv df. In this raster, the values were called layer, so that's what I need to call fill equals layer. And I'll run that command. And I need to specify the data equals harv. And I'm going to look for other errors. Yeah, when you're working inside these raster geometry, you need to specify the data. And it takes a minute because it's quite a large file. And then it'll plot our canopy height. So from 2 very large raster files, we calculated a third file for canopy height across this region. And these are meters, so we could calculate how many meters that is. 73, 1500, to 3,000, that's 1,500 meters, so 1.5 kilometers by, I'd have to do some more math there, but you get the idea. Each pixel is 1 by 1 meter. In addition to rasters, you often work with vector files. So vector data includes points, lines, and polygons. So maybe there's lines for roads and highways, or lines for trails, or polygons for the county or state or conservation area that you work inside. And shapefiles are one of the main formats of vector data. Shapefiles are a set of multiple files. They have the same name, but they have a different extension. So if we look in our plot locations, we'll see shapefiles. We'll see a series of shapefiles. They have the same name and they have different extensions. So .shx, .shp, .qpj, .prg, and these store different information. So the .prg is a projection. The dbf is a database of data, and we can access the attributes of these shapefiles similar to a GIS software program like ArcGIS using the $sign. So for example, it would be our file name, $sign, site ID to access the different attributes. So let's see an example of using vectors. To access this, we need a new library called rgdal, and you'll get this large message, which you can turn off. I'm always lazy. And if you haven't installed it, go ahead and install it using the install.packages function, and then call the library. Now let's create a new object called plotsharv using the read OGR function that's inside this rgdal library. And we need to call the name of our files, Neon Airborne. It's in the folder plot locations, and and we need to call the name of the file. So we want harv_plots, and remember R is case sensitive, so it distinguishes capital and lowercase levels, and we can run that line. So our plots have 5 features with 2 fields. Let's go ahead and use the base plot to look at these. So it looks like there's different points of trees. These are probably trees. Let's see if we can view our plots harv. So there's different information stored within the spatial points data frame. The data, which has ID and plot ID for 5. So these are different plots, locations, then their coordinates, and a bounding box, as well as information for the projection. So if you're not familiar with projection data, this is an example of different types of projections, and you need different projections because the Earth is 3-dimensional and maps are 2-dimensional representations of a 3D object. And there are different ways to transform 3D to 2D depending on where you are in the world. You might want to use different projections. So let's go ahead and plot our point locations or plot locations on top of our canopy height model. So we need to do a few things. We need to do the spatial stuff first. We have our canopy height model as a data frame. So we're going to want to use that. And we need to convert our plots as a data frame as well, because they're this special kind of data frame, this spatial points data frame. And we want them as a data frame that ggplot can recognize. So we've done the spatial part. Now we can plot. So ggplot, we want to call Raster, and we want that data equals canopy height model harv. Remember, this is the DF, the data frame version. And we want our aesthetics, x equals x, y equals y column. Fill, remember it was called layer. And on top of the raster values, we want to plot the points. Remember that ggplot works iteratively, so whatever additional geometries are plotted on top of the previous ones. So in this case, we want our data to be the plots data frame that we created from our shapefile. And we want x equals, let's look at the head of plots harv df, so we know the column names. So now it has x1, x2. This is Harvard, so this is the latitude. Oh my, 42 is the latitude, and negative numbers are the longitude. So we want x equals x1 and y equals chords x2, and we want the color of these points to be yellow to stand out from our raster geometry. And it takes a minute, and we get an empty plot with maybe a single point called color, and that's not good. Well, first I'm noticing that color was inside the aesthetics, and I need to pull it out. And nothing was plotted, so let's figure out what's going on. To plot two different data sets in this map, we need to make sure that their coordinate reference systems or projection are the same. And in this case, let's see the coordinate reference system of harv, our canopy height model, and the coordinate reference system of our plots. And they're different. So R doesn't know how to interpret that, and so it doesn't plot anything at all. So we need to change the projection. We can reproject our raster with project raster, or reproject our vector with SP transform. So we could reproject raster with project raster function, or reproject our vector with SP transform. Let's create a transformed vector using the SP transform function for our plots harv vector. And let's assign it the same CRS values as our canopy height model raster. Now, if we see the CRS of our plots, it's in the same as our canopy height model. And now we should be able to plot them on the same map. So let's go ahead. I copied and pasted we want to use this canopy height model data frame, the fill equals layer. Now, instead of plots harv df, we want to use this data frame we created. Oh, that's right, I missed a step. We need to create a data frame here. Remember, the steps are work with the spatial data, create a data frame, then use ggplot. So as.data.frame plots harv utm xy equals true. And now I can use the data frame that has the same coordinate reference system as the canopy height model. And I want to double check the column names. So I'm going to assume that they are the same. And instead of color happening outside, I want to pull it outside the aesthetics. When you specify a color inside the aesthetics, R understands that as some sort of grouping. When you specify color outside of the aesthetics, you're telling R what color you want those geometry to be. And I think we're ready. So now we've mapped these points, these plot locations on top of our canopy height model. Oftentimes you want to extract the values of this raster, for example, for the locations provided by your vectors. We can extract values. How about extract raster values at point locations? Let's call this plots underscore chm, and we can use the extract function to extract values of canopy height model for the plots harv utm vector. And now this is a vector. Let's see the values of that. So we have 5 values for each of these points of canopy height at the location of each of these points. The order of these values lines up with the order of plot ID. So let's look at our plots harv utm and the attributes. Let's access the plot ID attributes. So this is plot 1, plot 2, plot 3, plot 4, plot 5, and these, the values that we extracted, line up with those plots. So let's combine these extracted values into a data frame. So let's build a data frame. And let's create a column called plot number, and that'll be plot harv utm $plot ID, and then the second column will be called the plot value, which will take on the values in this vector we created, plots underscore chm. And now let's look at our data frame. So we have the plot number and the plot value. Oftentimes you want values, you want, like an average of values surrounding a point, not just a single pixel that the point lands on. And to do this, we can modify our extract function using a buffer of the number of pixels. So the buffer argument gets values for all pixels within some buffer distance from the point. So in this case, it's 10 pixels. So this returns one value for each pixel within the buffer region. Oftentimes you want to create maps of point data. So let's see an example now of a map, and we can access maps in the maps package. So install it if you need to, and then call it using the library function. Let's load something called US map using the map data function, and it recognizes countries by their universal abbreviations. And you can look those up if you're interested in a specific country. And if we looked at this object we've created, either in your environment or by printing it out here, you might want to use head here, we can see that these are actually stored as polygons with different coordinates, but it's already been converted to a data frame. This map data function uses the as.data.frame function. So we have the coordinates first, then what group they belong to, and the order. So the group identifies unique polygons. The order identifies how the points in each polygon are connected. So let's draw a polygon illustrating the points, edges, and order. So let's call our ggplot. And because these are polygons, we need to use the polygon geometry. And our data is this object we created, US map. And our aesthetics are X is longitude, Y is latitude, the group equals group, and let's fill these using a gray color. All right, so the polygons here, we can see the outline of the United States, and it's a little wonky, so let's use a built-in coordinate format using Quick Map. So this projects a portion of the Earth in a kind of quick and dirty way so that the coordinates are aligned and you don't have this weird distortion, right? Because in this area of the world, 1 degree of longitude is not the same distance as 1 degree of latitude. Now let's try adding other data on top of this map. Let's get data for species occurrences using the SPOCC package for species occurrence. I don't think I've ever installed this, so I'm going to have to use the install.packages SPOCC. And while that's loading, I might clean this up a little bit. I'll comment it out, and it might take a minute. All right, I might clean my code up while I'm waiting. All right, so let's create an object called dogbif, and let's call the OCC or awk function from this species occurrence library. And it expects an argument called query. Let's query this specific species name, Dipodomus wardii, from different sources. In this case, we want to call gbif, and we want to limit it to 1,000 occurrences because there could be millions of occurrences. If you want, you can Google gbif. It is a global database of occurrence records from everything from natural history museums to herbaria. It has all sorts of taxa. Has coordinates equals true. We want to use that argument because we want to pull in records that have x and y coordinates. And do data, we want as a data frame this. It returns an object in this format. This is a large kind of occurrence data frame, but we want a normal data frame because it has tons of information in there. You can see that one of those attributes is called gbif, which has metadata as well as the data itself, which is what we're interested in. So this is where we have the latitude and longitude for the occurrence records for this particular species. So that's what we want. So we need to create a data frame from this, inside this larger, more complex object. And the data is located in this gbif list, and it's called data. So you can see that here. So gbif is a list of two. It has one list called meta, and another list called data. Now if we view this newly created object, now it takes on a data frame that we can use for ggplot. And if we scroll across, we see all these kind of Darwin cores, what they're called, Darwin core column headings. And somewhere in there is the latitude and longitude. Let's map this by calling our ggplot. We want the polygon of our US map, and we want those aesthetics to be the same. You could copy and paste them from above. And we want the fill to be the same, gray. And now we want to map those point data, geom point. Our data is do underscore data. And the aesthetics, now I need to see the names of our do data object because it appends this large name. So I'm looking for something that's called latitude or longitude, so I can copy and paste it and not have to worry about typing out this long name. So X is this long thing, Y this long thing, and we need to add this chord quick map to avoid that distortion. And I misspelled it, and I'm also missing, I accidentally closed it here, closed the parentheses there before the fill. Okay, I should be ready now. So now we're plotting the occurrences, these point occurrences for this particular species on top of our map. There's two more things that I want to demonstrate. The first is this conflict that you may come across when there's two functions in different packages that are named the same. So let's see an example of this. dplyr and raster have these different names. So you can see the following objects are masked from package raster. So intersect and select. That's because these two packages have the same name functions, and this can cause errors, and it's hard to figure it out, and then you realize that it's because it's the same function name and R doesn't know which function you want to use, so it spits out an error. Let's see an example of this error. If we wanted to select specific, and I'm not even going to try to type it. So if we wanted to select the latitude for all of these occurrence records, let's call this first, then the raster, and it works, but I was hoping it would spit out an error. For the purpose of demonstrating the type of error that you would receive, I had to unload these libraries and then load them again in this order so that the select function in the raster package would overwrite the select function in the dplyr package. Then when I go to use the select function, which is you might remember it from our dplyr tutorial, then the function is unable to find an inherited method for function select. And that's because select is in both libraries that are called. So you would need to specify using this notation where you're noting the package name followed by these two colons. And now the command works like you expect it to. The final thing I want to demonstrate is how to go from a data frame to a spatial points object. A lot of times you'll be working with a .csv files that have two columns called latitude and longitude, and you want R to understand that data frame as a spatial points data frame. So let's first build a data frame called doDateSpat. No, let's call it doDF. And in that we want to create a data frame using this subset notation from our do data that we've created. Let's build a data frame using these square brackets. Inside we want to call these two columns. We want to call, I'm going to copy and paste the two column names for longitude and latitude. And I'm going to run that command. Now I'm going to look at doDF. So this would be a typical .csv file you've imported. It has two columns, latitude, longitude. Maybe it has additional columns with other information for each of the observations. And now I want to turn that into a spatial object so that I can do extract values for each of these points from a raster. So to do that, let's call this doDateSpat for spatial. And we can use the spatial points data frame. We'll call it doDF. And we need to give it a projection. So project for string. And we want it to be the same projection as this plots harv object. Maybe we're interested in this species that's found often in this plot, and we want to know the larger distribution. So I want to give it the same projection. To do that, we would add this call to the project for string argument. And data is missing. So let's go ahead and specify data equals, and the chords are missing. And I had to look at the help file for the spatial points data frame because I forgot the order of arguments. So it expects the chords argument. So you need to tell R where those coordinates are located. And in this case, they're the first and second columns of our do_df object. And now I can run this command, and now I have a spatial points data frame that I could use to extract values at these locations based on another raster. So if you're importing a .csv file with longitude, latitude, and you want to extract values from a raster object at each of those point locations, you would need to first convert it into a spatial points data frame, designating the coordinates as specific columns in that original data frame, and designating a specific projection. So in this case, we gave it the same projection as an existing object. So now you would be able to do things like reproject and extract values from rasters. So go ahead and practice these new functions. We see a lot of new packages this week, and get some exercise making some cool maps.